Greetings. This is the first of 3 narrated PowerPoints covering plate tectonic theory. So as you learned in Chapter 1, plate tectonics proposes that the Earth's outer brittle shell is broken up into these mobile brittle plates that slide around atop a more mobile interior, that is a weak plastic interior. Whereas the plates themselves are brittle and breakable, the interior of the Earth directly underneath the plates is weak and highly plastic. It behaves more like silly putty. Okay, the essence of plate tectonic theory, as you also learned in Chapter 1, is that the plates can interact in only 3 possible ways. They can move apart from one another at divergent boundaries. They can move together, that is, towards one another, at convergent boundaries, and they can slip sideways past one another at transform boundaries. As we'll get into, we now know that it's ultimately gravity and to a lesser extent mantle flow that drives plate motion. And the plates don't move very fast by human standards, only a few millimeters to a few tens of millimeters a year, roughly at about the rate that your fingernails grow. Importantly, as we'll learn, it's not just the plates that move, but the boundaries between the plates also migrate, even as the plates themselves migrate. So there's a lot on this slide. I encourage you to kind of slow the narration down, stop the video where you need to really extract the most important information from this slide. But the take-home message here is that we can think of the layered Earth in 2 ways. We can speak in terms of compositional layers, where we distinguish from the outside to the inside, a crust, a mantle, an outer core, and an inner core. And you'll notice that density tends to increase with depth, and also that the different compositional layers are made out of different stuff. On the other hand, it's actually more convenient for plate tectonic theory not to describe Earth's interior in terms of compositional layers, but in terms of mechanical layers. And for our purposes in this course, we'll focus on 2 main mechanical layers, including the lithosphere, which is what the plates are made out of. The lithosphere is literally what cracks and breaks up into plates. And then that underlying, more mobile, highly plastic layer called the asthenosphere. The asthenosphere entirely occurs within the mantle, whereas the lithosphere includes portions of the crust and the uppermost mantle. So really important to appreciate here on this slide that when we talk about the plates, the tectonic plates in plate tectonic theory, that they're really lithospheric plates, not just crustal plates. Here's a quick map of the outlines of the plates. You've seen this before. And here again, don't lose sight of the fact that the lithosphere includes the crust plus the uppermost mantle. So you can call the plates tectonic plates if you want. Better yet, call them lithospheric plates, but in no way, shape, or form should you refer to the plates in plate tectonic theory as crustal plates. And the reason is that the plates aren't synonymous with the crust. The Earth's crust is certainly part of the plates, but we generally like to avoid the term crustal plates because it's misleading. Almost nowhere does the crust move independently of the mantle. Okay, very quickly, and you learned this in Chapter 1, but I just want to reiterate here and then go into a little bit more depth than we did in Chapter 1. Alfred Wegener, of course, was the originator of a precursor to modern plate tectonic theory. Wegener called his earlier model continental drift. And Wegener, of course, came up with compelling evidence that the continents actually moved. For one thing, he noticed that the continental coastlines seem to fit together really nicely like pieces of a puzzle, but it's not just the coastlines, it's distinctive rock bodies that match up across widely separated continents. And it's also distinctive occurrences of fossils that can be mapped across widely separated continents. In many cases, these continents are separated by thousands of kilometers of open ocean. And so Wegener's continental drift model nicely explains how you can get land-dwelling creatures, literally the same species of creature on continents that are now widely separated by open ocean. So the fossil evidence and the ancient rock evidence and the coastlines really all support Wegener's idea of drifting continents. There's even more evidence, though. Wegener noted that there's evidence of distinctive glaciation that occurred on the order of 300 million years ago all over the world. We see it in South America, in Africa, in India, and even in part of Australia. Interestingly, though, when Wegener put all of the continents back together to form his hypothetical supercontinent that he called Pangaea, he noticed that what appeared to be separate glacial deposits on widely dispersed continents actually turned out to be a single ice sheet that formed kind of in the middle of Pangaea and spread out to what are now all of the different continents. The arrows in this left-hand diagram represent glacial scratches. As you can see here, those glacial scratches are called striations. And really strangely, in some places like Africa and South America and India, the glacial striations indicate that the glaciers moved from the ocean up onto the continents. Well, that's strange indeed, because that never happens. And yet, when Wegener reconstructed his Pangaean supercontinent, he noticed that, in fact, the middle of this ancient ice sheet was roughly where I'm putting the dot right now, and the ice sheet just moved outward in all different directions on what used to be the Pangaean supercontinent. So, in other words, the continental drift hypothesis nicely and elegantly explains the distribution of this 300-million-year-old ancient glaciation. Likewise, with ancient climates, what's fascinating, and this was particularly compelling to Wegener himself, what's fascinating is that when he put all of the continents back together, puzzle piece style, he could arrange zones of ancient climate into distinctive bands. And that was important for Wegener, because what he realized is that mobile continents were moving through stationary climate bands rather than the other way around. And so the ancient climate evidence was particularly compelling for Wegener. Wegener also noticed, though, that there's evidence supportive of continental drift if we look at the distribution of ancient mountain ranges. And here, if we look at both sides of what's now the wide Atlantic Ocean, of course, we have what appear to be separate mountain ranges kind of straddling both sides of the Atlantic Ocean today. But when Wegener reconstructed Pangaea, he noticed that these separate mountain ranges, in fact, would have represented a long, continuous mountain range that ran right down through the middle of Pangaea. So to summarize then, all of these different data sets can be nicely and elegantly explained in terms of moving continents, including ancient glaciation, ancient climate, and ancient mountain ranges. So this is what Wegener thought was probably happening to explain all this. On the order of 200 million years ago, or maybe slightly before, Wegener's hypothesis is that all of the now separated continents were back together into a single supercontinent that Wegener nicknamed Pangaea, which means all Earth. And then the entire history of the last 200 million years or years or so, geologically speaking, has to do with the migration of the different continents into their present positions like they are today. And here's an animated version of what Wegener envisioned. So there's the Pangaean supercontinent. Notice that it's breaking up, and the various continents are going their separate ways. South America is splitting off from Africa, and North America is splitting off from Asia and South America and Africa. And I don't know if you noticed, India zoomed up from the southern hemisphere to collide with southern Asia. Okay, well, before we leave Wegener aside and move on to modern plate tectonic theory, it's really important to note that continental drift and plate tectonics are by no means the same thing. What Wegener thought was happening is that mobile continents were plowing through stationary oceanic crust. In other words, it was only the continents that moved in Wegener's model. Whereas in modern plate tectonic theory, everything is moving. There's literally no point on planet Earth that is stationary. Every point on planet Earth is part of a plate, and therefore every point on planet Earth is to some degree moving around. And the other modification that modern plate tectonic theory made, really the important update with respect to continental drift, is we now know, of course, that the plates, the lithospheric plates in plate tectonic theory, include both the crust and the uppermost mantle, not just the crust. And so that's why we speak of lithospheric plates, not just crustal plates. But certainly a lot of the evidence that Wegener cited for continental drift also counts as being supportive for plate tectonics. Okay, one last slide, and then we'll end this first of three presentations on plate tectonic theory. So in terms of some of the jargon that we use to describe the plates, we sometimes make a distinction between a continental plate and an oceanic plate. And this is just helpful terminology. Think of a continental plate as just a plate with continental crust embedded in the top of the plate. By contrast, an oceanic plate is just a plate topped by oceanic crust. And as you can see in this diagram, it's actually most common for plates to be both continental and oceanic. And again, the all-important take-home message here is that the plates in plate tectonic theory are brittle. That means they break up. That's why they've broken up into plates. And that the plates are lithospheric, not just crustal. The plates consist of crust plus uppermost mantle. That's what we call the lithosphere. And then directly underneath the lithosphere, we have this highly plastic zone entirely within the mantle that allows the plates to move around on top.